interrupt me if it is both too simple and if it is too difficult. So I'm flexible, I can change my schedule as you wish. I have actually thought to go first, because Susa asked me about that, very basic into the processes that are included in biogeochemical modeling. For some of you it will be very boring, you can do something else, reading emails or whatsoever. But then explain a little bit how these biogeochemical models are built up, and then an application, why we are doing this, and this is for future climate projections. And that will come after lunch, so it's 2 times 45 minutes, but please interrupt if you have questions immediately. So first of all, I would like to start with some observations. And here you see records at the Gotland Tube Station in the Baltic Sea. It's actually temperature, the variables are temperature, salinity and oxygen from 200 meter depth. And what you see here is that the variables, the temperature and salinity and oxygen are somehow correlated to each other. So if you have these little peaks up in salinity, then you usually have also a peak up in oxygen. Then you have kind of decrease in salinity during some period, and then an increase again. And those of you working with the Baltic Sea know what this is. These are stagnation periods. There are saltwater inflows into the Baltic deep water. And when that happens, this water is usually oxygen rich, because it is water from the surface in the entrance area, and it's interleaving according to the density of that water into a certain depth. So here in this example from 200 meter depth, bringing oxygen rich water and ventilating the deep water. So if you want to understand biogeochemistry in the Baltic Sea, it is almost impossible to do it without understanding the physics. Both variables, well, both parameters, the physical and biogeochemical, are very strongly interlinked with each other. This is even true for temperature, although it's not so clear. It can be that an inflow happened in winter time, then it's cold water, or it can be that's more an autumn inflow or even a summer inflow, then it's usually smaller ones. Then the temperature is higher. So there's also a some linkage, but not really a clear correlation to temperature as well. And this is very important to understand. So therefore, to understand the biochemical cycling in the Baltic Sea means to first understand the physics. An important driver of biogeochemistry, or stressor, is actually eutrophication. There are others, pollution, overfishing and so on. But eutrophication has once by, I think it was the Swedish EPA, ranked as the most important stressor. It means simply that in the water column the nutrients are increased. But it is often also used together with increase in primary production, lack of oxygen, severe reduction in water quality, although this is not, at this stage, not very well defined. So what does it mean? There is an additional or elevated supply of nutrients from land into the sea, and the consequences like bloom of cyanobacteria are connected to this nutrient, external nutrient supply. And the consequences are, for instance, that the whole stagnant or the whole deep water in the Baltic Sea is getting well, hypoxic or anoxic. So that means a lack of oxygen, with the consequences that we will discuss later on. So therefore, this is actually the motivation somehow why these kind of models have been done. I heard that Fredrik Wolf has given me a lecture as well, so for management of the Baltic Sea, planning of nutrient load reductions in relation to certain targets in the sea. that is one, one major motivation for building up these kind of models that I want to introduce. Both the areal extent and volume of hypoxia and anoxia are elevated to levels never recorded before, and people usually say, okay, that's due to the external nutrient supply. And here you have some maps of the Baltic Sea where you see the areas that we call anoxic, so oxygen concentration smaller than 0 simple, or hypoxic smaller than 2 milliliter per liter. This is just a kind of definition. So as I told you, the physics are very important, and here the Baltic Sea is really somehow special. It's a semi-enclosed sea, but built up into a chain of basins that are connected by narrow and shallow. So we have a fjord-like characteristic. Although the Baltic Sea is not an estuary, it has an estuary circulation, or estuarian-like circulation. But it's not an estuary in the classical definition because it's not two-dimensional. It's large enough that the Coriolis parameter, the Coriolis force, plays a role so that the wind-driven circulation overlay the estuarian circulation. It is shallow with a mean depth of 54 meter. The water exchange is restricted. That means a long water residence time. The freshwater supply is large, so therefore we have in the very north, say 2 PSO, and in the very east, in the river mouth of the river Neva. And then there's a gradient towards the Kattegat, where we have open sea salinity condition, oceanic condition outside the mouth. And that means a brackish, highly stratified water body. So let's go more into the physics and how to build models that describe these physics. Again, we have to the left the topography, to the right the typical salinity profile from the center of Baltic Sea. It looks like this, that you have first the vertically homogeneous layer due to mixing, wind-induced mixing. It's homogeneous. So this is salinity, but you can also display here density, it doesn't matter. And then you have a jump layer, which is called the halocline, and then the stratified deep water with weak mixing. And that is actually special for the Baltic Sea, that there are no tides, or the tides are very unimportant. So therefore the physics are very much different than from the North Sea, for instance. And here you have a sketch of the circulation, the mean circulation. It's very hard to detect the mean circulation because the variability is so large. The sea is shallow, so the influence from the atmosphere, from the variability of the atmosphere is large. So if you go out by ship and measure currents, then it's almost impossible to detect this mean circulation. It's only possible from theoretical reasons to determine such a circulation, and from models actually, where you have long records that you can average over all the high variability induced by the atmospheric forcing. We have the Coriolis impact, so on the northern hemisphere it's a cyclonic gyre in the surface. We have the supply from the rivers with water, and salt water inflows from the North Sea, that are the red arrows, into the deep basins, following just the topography into the Gotland Deep and Lanzarote Deep here. That's the schematic view, how we need to describe it. So one can have two point of views. One is, okay, we have almost homogeneous conditions per basin, and then we build a model that connects different basins, and the equations that describe the transport between different basins are straight flow dynamics. So simplified exchange formulations between the basins. Or you argue, okay, I want also to understand the circulation within the basins. This kind of horizontal and vertical circulation. Therefore, you need three-dimensional models, and that is what I want to discuss here. What should be included in such a three-dimensional model? Okay, here you have all the important, sorry, this is not Swedish, time and spatial scales in the sea. Here you have the axis for the time scale and the spatial scale. You have sound waves, wind, sea, microturbulence, and then you go to tides and the overall large-scale thermohaline circulation. Circulation cells, these are the cyclonic gyre that I described for the Baltic proper. Then you have eddies, fronts, and so on and so on. The question is, well, in principle you want to have all included in the model, right? But, and the tricky thing is that all the different scales, all the different processes interact together. So in principle, to have a perfect model, you need to include everything. And that is possible theoretically, described by the Navier-Stokes equations, but it is very much unrealistic in relation to today's computer power. So typical ocean models have less degree of freedom than the real ocean, and usually just this upper part is described. So only the circulation and maybe the thermohaline circulation, although this is also very much described by small scale processes like diffusion and turbulence. But this is something that is included, and high resolution three-dimensional models include even eddies, but not all the other stuff. And that means we need to somehow parameterize these processes. I would like to give you an example how the ocean looks like. And as there is no mean circulation in the Baltic Sea, I have borrowed this from the North Atlantic. So you all know that there is the equatorial current system and the boundary currents, the Gulf Stream extension. But it's not a continuous stream. So there's a lot of eddies and spatial variability ongoing. And you can argue, okay, maybe I do not need this in my model. But studies have shown that the horizontal eddy transport is for some processes quite important. So therefore, there is an aim to have an eddy resolving three-dimensional model like this one here from the flame model from the group in Germany and Kiel. You can also look in. This is actually just a marker, an H tracer that is injected at the southern boundary. It is only here to give you an impression about the time scale, how the signal is propagating from the southern boundary in this model case, then interacting with the equatorial current system and then transported by eddies in this current system towards the north. So there's a lot of small scale features ongoing in the ocean. So the model that I here describe is based on a person called Kirk Brine. He wrote in 1963 a paper about the nonlinear model of an ocean driven by wind and differential heating, and introduced in principle something we call today the primitive equations. And what he did is putting up a set of differential equations together and solve an initial value problem for the ocean. That was the first time, and since then these models have been developed further and further. So the primitive equation include, and this is really for the large-scale circulation models, it includes, as I said, a set of partial differential equation for the salinity, for the potential temperature, for the velocity, and for, temperature and salinity are of course linked together by the density equation. So, and these equations are simple consequences of mass balance, salinity balance, or the balance of matter, momentum. And the first and second thermodynamic law. If you build this, so I would not like to bore you with equations, okay? Therefore, this is just qualitative. You have some problems, and this I would like to discuss here. These models cannot be, as we discussed before, really the complete Navier-Stokes equations. So therefore, there need to be reduced degree of freedom. So some approximations that I want to discuss, included in the primitive equations. The second is that we have not the possibility to have a continuous description of the ocean, but a discrete. So we introduce finite differences due to the grid that we put into the ocean, and then we need to parameterize those processes that are important but that are on the subgrid scale, because we need them for the description of the large scale. So these are the approximations that are included in the primitive equation. First of all, it's an unelastic approximation, so the sound waves are not included, and this is actually something that you can choose a reasonable time step for your model. Then there's the Boussinesq approximation, uncompressible ocean that has some consequences. We have something that we call the Reynolds separation. So we develop this equation by separating the variable, and for instance the velocity, into a mean and the fluctuation part. And if we calculate then the some average over the fluctuative part, then it's by definition 0. And if we do this, it's actually important to have to build in a closure to the processes that are not included. And finally, the shallow water approximation, and that means that the depth of the ocean is smaller than the radius, and that the depth is also smaller than the horizontal scales. And here is something, well, it's called also sometimes the traditional or hydrostatic approximation, and that means that convection, for instance, in the ocean, and short gravitational waves are removed. But they are important, for instance, for for deep water mixing, for the deep water circulation. So they need to be somehow included afterwards. Then the equations are discrete. So we have some grid points. Well, it is simply a grid, a horizontal discretized grid, and it could be whatsoever on a sphere, or, well, that's the usual thing, a regular grid, horizontal grid, and you solve the equations at these discrete grid points. If you do that, you develop the functions at each of the grid points, and here is an example. It's called the variable u. For instance, velocity, and if you want to calculate a derivative of that, for instance, if you calculate du dt, the change with time, or the change in space, and you expand the series at the grid point x to delta x, that's the distance of your grid, according to a Taylor series. So simple mathematics, and you do it to the right and to the left, and then you can have a forward derivative, like here. So you calculate it at the point x plus delta x, minus at the point where you are, divided by the grid distance. And then you have something, the rest, and the rest is of the order of x. And that is actually not so good, because x is not very small, or can be quite large according to your computer power. So this gives you an error in the equations. So this is not good, so therefore people usually use center difference, that you develop it to the left and to the right, divided by 2 delta x, and then those terms vanish, you only have those. So the error is of the order x squared. And you can even do it more advanced if you calculate advection, that you have advection schemes that are of the 3rd order of accuracy. This gives you an impression how these equations in principle are built up. So you discretize them according to this scheme, and you have a set of discrete equations, but always with an error. And the problem is, well, if you can use the grid as small as possible, then the error is small, but that's not possible. The model that I'm describing here, it's the RCO-SCOBI model, and it has a horizontal grid distance of 2 nautical miles, so 3.6 kilometers. And the third problem I would briefly sketch here is the parameterizing of subgrid scale processes. What are the consequences of this grid approach? Let's take the example of the geostrophic eddies that you have seen in the animation before. Here is a relatively old figure from a model for the world ocean. It's the model POP from Los Alamos. And what you see here is the grid that is used at that time, so it's from a publication more than 10 years ago. So they used the grid of 0.1 degree or 0.28 degrees. So that's they have a fine resolution and a high resolution and coarse resolution model. And usually to take into account that the Rossby radius of deformation that describes the eddies is smaller in the north, these grids are multiplied with the cosine of the latitude. So therefore, it's not just a constant curve here, the grid distance, these two, but it is getting smaller towards the pole. So we have here 20 degrees south and 70 degrees north. And then you can also paint here the display the Rossby radius of deformation. That's this solid curve. It is very large, close to the equator, so there's no problem. But if you go further to the north to Baltic Sea conditions or even to Arctic conditions, then you have a problem, at least with the coarse resolution version of this POP model. So there is a certain resolution really necessary of 0.1 degree, at least in this example. And what that means really in terms of how to represent eddies, you can see here on these three panels where different resolutions of that model have been used. To the right, that's the reality from satellite observation. It's actually the Gulf Stream separation at Cape Hatteras, where you have a lot of eddy activity in the ocean. And with the 12-degree ocean model, you do a pretty good job, at least qualitatively. This kind of variability looks like the observed one. But if you go to a quarter degree or just 1 degree, which is still the case for global climate models, so it's not completely out this coarse resolution actually, then you have not really this variability at Cape Hatteras anymore. The Gulf Stream is actually, well, not really extending to the north like observed. It's more going towards the east. So keep this in mind if we talk about global climate models. Then the Gulf Stream is represented like in this sketch here, and not really having the eddies included. Parameterizing of turbulence. Turbulence is very important for the mixing. So we are now in the lower range here, the microturbulence and boundary layer turbulence that need to be described. Yes?
Excuse me, if you go back one second. The Langmuir cells,
yes.
Is it the wind sea or is it somewhere between boundary layer and wind sea?
I would like to put them
okay.
here.
Yeah.
Is that a special reason why you are asking?
No,
are you
I
working
just,
with Langmuir?
no, but I just remember. I remember them.
Yeah, well, they are quite important for the mixing in the upper layer, actually. And some of the more advanced turbulence models today have them included. But traditionally, they are not included. So it's not so long time ago that it has been recognized that they are important for describing turbulence and the surface layer. So these processes sketched here are also sketched in this. Here you have the Langmuir circulation, the rows. You have shear-induced turbulence breaking internal wave, which is very important for the mixing in the deep Baltic Sea, deep water. You have convection. I told you that it's not included, it needs to be parameterized. So we have for all these processes more or less good parameterization in our three-dimensional model. It is not the Navier-Stokes equation. In principle, you can do it. In principle, you can add correct mathematical formulation. But as the grid resolution is rather coarse, usually in this kind of models, it needs to be parameterized. And if you then look at the Baltic Sea, I showed you the very first figure where we argued that the ventilation of the deep water is very important for the biochemistry. How to describe that? So the high saline seawater is coming over the cells, flowing, because it's heavier water, into the deep, and then according to the density, it is interleaved into a certain horizon. And during the way from the cells into the deep, there's entrainment. So due to turbulence, brackish water from the Baltic Sea is mixed into this more saline water. And this is a very important feature of the Baltic Sea, because that's the explanation for the overall vertical estuarians-like circulation. It is based in the models on parameterizations, on certain assumptions on how this entrainment, for instance, looked like. So the strength of this overturning is actually depending on more or less good parameterizations. How to describe this inflow? Well, we have a discrete grid, also in the vertical, not only in the horizontal. Think about this as a sketch of the original topography, and then you put in some grid cells, and then you have to decide, okay, is it half a grid or the full grid? Nowadays you have actually partial grid descriptions, but take it very simple. So you have a step-like topography at the end if you use a traditional depth coordinate system. But this is not the only representation. You can also use isopycnic coordinates, that means following density coordinates, or topography following coordinates, sigma coordinates. And then you may guess what is the best for the Baltic Sea.
Perhaps sigma.
Yes, very good, because of the inflows. But sigma coordinates have a lot of problems with mixing, with the parameterization of mixing. So these are very good for process studies. If you have the high solar plume following the topography, flowing into the Baltic Sea, then sigma coordinates are really the best. But if you then integrate on long term, where the mixing is getting important, these models are actually have severe problem. So there's no perfect grid, actually, that's the answer. All of them have shortcomings, advantages and disadvantages. And our model is actually a traditional level model. Okay, let's go to the biochemistry. And the idea, I first rushed through the processes, so I assume that you all know them, but it is just a listing of those processes that are in principle included in biogeochemical models, and then I would like to sketch how our model looked like. So the starting point is phytosynthesis, primary production of phytoplankton based upon the transformation of carbon dioxide and anorganic nutrients to living organic matter. And for that you need sunlight, and oxygen is produced. So that should be included. Phosphorus and nitrogen in the Baltic Sea, limiting nutrients, are important to describe. in inorganic and organic forms, and suspended, particulate and dissolved forms, bioavailable and inert forms, and pools in the water and in the sediments. So we have the important inorganic nutrients are DIN, dissolved inorganic nutrient, and dissolved inorganic phosphorus, DIN and DIP, ammonia, nitrate, phosphate. And then also important for cyanobacteria, for the ability of cyanobacteria to fix is the molecular nitrogen input from the atmosphere. Due to the motivation that I sketched in the beginning, we want to describe also cyanobacteria, because it's one of the consequences of eutrophication. And this is a little bit complicated. It summarizes all the processes here somehow. We need not to go in too much detail, because I assume that you know the basic mechanisms. But important is that you have the water column, you have the productive surface layer, and you have the sediments. So the models also need to include in the shallow Baltic Sea the sediment, the interaction between the pools of nutrients in the sediment and the water. This is very much different from the large-scale world ocean. So we have the production of organic matter. The organic matter is dying, remineralized, and then it depends very much on if you are above the redox line, if you have oxygen available, or if you're below. And then you get important processes are denitrification and anamox, and finally burial. What do we have more? Well, we have pools of nutrients in the water, physical processes, so these are the biochemical processes that I sketched, but of course the physical processes are important. You consume during the spring room, for instance, the nutrient, and the supply of nutrients is only in the vertical. So therefore, the vertical mixing and reduction processes are very much important as well here, and the lateral transport of nutrients. So we can see the biochemistry as a reactor. So we have in the box the life, and we put in nutrient and oxygen. We have light, and out is coming nutrient export. So we have the external nutrient input, internal nutrient cycling and biochemical processing, internal nutrient removal, like denitrification, and nutrient export. What will happen if we skip the processes in the box, in the reactor? If we take away the biogeochemical processing, and if we take away the internal nutrient removal, well, it will look like this. These are model experiments now for some period. It's actually 100 years of integration. It is for the nutrients nitrate, phosphate at the Gotland Deep, in the surface and in the deep water. And the red dots here are the observational data. The levels are 0 and 200 meters. And if you take away the biogeochemical processes, the content of nitrate will increase. Then there will be maybe some kind of equilibrium after longer than 100 years, because you have export from the Baltic Sea. If you do the same in the deep water, it looks pretty much the same. The characteristic for the phosphate is a little bit different, that you have a much shorter time scale, and then the phosphate is transported out and you come faster to an equilibrium. So the biochemical processes are very much important. If you do not include it in the model, then you get something completely unrealistic. These kind of experiments are nice to get some feeling for the time scale involved. Looking more into the vertical and in the horizontal structures of nitrogen and nitrate and phosphate distribution, again at Gotland Deep. It's from the shark database nitrate, here you have DEF, and then from the 1980 to 2004, and the right panel shows phosphate. So we have a lot of nitrate in the halocline, and then depending on major Baltic inflows, you can replace even the deep water. So strong gradients in the vertical and also for phosphate, where you have the pools in the deep and a lower concentration in the upper part. That need to be described. And in the horizontal, and therefore again the motivation to use three-dimensional models, the concentrations in the left we have DIN and to the right we have DIP are highest close to the mouth, to the supply. So this is how it looks like in the horizontal. This needs to be described as well. And finally, we have the vertical seasonal cycle. The water temperature, the stratification is very much important, and as an example, here we have nitrate. During summertime, we have the nutrient uptake, and it's very important to get in the models the gradient between the lower part and the deeper part, because the supply of the nutrients is coming from below. Driven is everything by the solar radiation, and then we have typical observed phytoplankton records or biomasses here, that you have a peak during the spring bloom and later on a secondary peak during summer and autumn. And finally oxygen, a strong gradient also here because it's supply from the atmosphere. And then you consume it, so actually here we have the halocline, below the concentration are much lower and anoxic conditions during stagnation periods. Important is, and that I will come back after lunch, is the oxygen saturation concentration, which is temperature and salinity dependent. So if we have warmer water, then the oxygen saturation concentration is actually smaller. And that is actually important to understand the consequences in changing climate. The material, organic material, is sinking towards the bottom, so we have then an active top sediment surface layer, and another part, the old sediment left below the active surface layer, so then we call it permanent burial, and that need to be included in the modeling. If you look at how the sea bottom looks like, this is a map, then you can distinguish between accumulation, transport and erosion bottoms, or also different types of bottoms. So in principle these need to be included in the modeling as well, because you have the production in the coastal zone, and then you transport the material with the process of resuspension. I will explain in a moment what that is. So the deeper part, and then you have accumulation in the deeper part where the influence of the waves is not so strong anymore. And this is an important, lateral transport of from the production areas into the deep. So how does it work? It's actually the key is here the waves. So our model has a simple wave model included. You calculate the wave speed at the sea bottom, you combine that with the current speed and calculate the critical stress. And if the critical stress is about, or you calculate the bottom stress, so then you define a certain critical threshold. If the the bottom stress is above this threshold, and this depends, of course, of the material, of the grain size, and so on and so on. Then we assume it's a resuspension in the model happens. That means that you take everything up that is stored in the active layer of the sediments, so nutrients and nitrogen and phosphorus, and transport it with the currents in the water column into the deep. And then it's sinking again if the influence of the waves is decay and is sedimented there. And actually we can show with our model that we have the right horizontal transport like it is observed, and that we get the pools of the nutrients in exactly the position where we want to have. So in principle we do not have something like it's here shown, so the separation between sand, bedrock, hard clay, mud and so on. But what we can do from the characteristics of resuspension characterize in principle erosion, transport, and accumulation bottoms, and get very similar maps than those that are observed. Philip?
The accumulation bottoms, are they mostly below the halocline? It looks like, especially in the Baltic Sea.
Well, it's actually below the layer where the wind waves work, and that is 70 meters, and that coincides very well with the halocline. But it might be during very, very strong storms. It could be that resuspension occurred down to a depth of 80 meters or so. Yes?
How much of the sediment, of the stuff sedimenting, would you say reaches the accumulation bottoms, and how much stays in the other areas, in the shallower areas?
Well, it's a good question. I have this figure not with me, but the measurements actually show.
You can Markus wipe it if you want the board.
Maybe I can use this later on.
You can quickly put the.
I just put down, so the pools on the, of nitrogen, actually it's a very simple curve, that you have the production in this shallow, and then you have a maximum in 100 meter depth, and then it's decaying. So the curve looks something like that. So the pools actually in the Baltic Sea are around 100 meter depth. So you produce in the sediment. So you produce a lot of the material that is produced in the coastal zone is actually not sedimented in the coastal zone, but in 100 meter depth. So I cannot say you concrete numbers now.
It's sedimented in the coastal, but it's transported to.
Yeah. Okay. So the first sedimentation occurs, of course, in the sediment, but then you have individual wave-induced suspension events, and then it's transported further. So the end storage is somehow in 100 meter depth. So that is the
Do you mean sites that are the 100 meter deep, they have the highest amount of nutrients there? And station sites that are 200 meters, they have less than 100 meters.
That is exactly what I wanted to say. Thank you. So you have some kind of not steady state here in the coastal zone, of course. But if you paint this like here, such a profile, so the steady state solution would look like something like this.
And that's interesting because that's the area where the redox kind shifts a lot.
Exactly, exactly. And therefore it's very, very important to have this correctly in the model. Yeah. Because if this pool is too high up, if you, for instance, do not have resuspension in the model, then the dynamics are completely different because the oxygen concentrations is different, or if it's low.
So the halocline is determined by mixing more than by the amount of inflow.
Both. I mean, it's equilibrium of the mixing. So the depth, in which depth is the halocline? It's the influence from the atmosphere, but also from the transport from the lateral, from the sills. Because when we have, for instance, saltwater inflows, there's a movement of the halocline. We can recognize this from observation. So if there's a big saltwater inflow, the whole halocline in the Baltic proper moves up. And then you have erosion by the mixing from above, and then with time it's lowering again. So it is breathing somehow. And this is about 20 meters, 30 meters. The halocline can change vertically. So it's some kind of two processes that determine where you have the halocline. And this is very much important for assessing the nutrient pools. Sorry?
No, just
okay. I think I jump over this because these are, we can take this one here. This is quite important. The observation. So the biogeochemical cycling in the models include the nutrients that are limiting, phosphorus, nitrogen, and oxygen. And if you look at observations, then it's very clear that for phosphate and oxygen, it's anticorrelated and correlated for nitrate. So if you want the first test of your biogeochemical cycling, you can actually use look if this relationship hold. And well, I jump over this. Yes, of course.
About what time scale is the sediment focusing? If the spring bloom comes down, for example, will most of it have time to remineralize before it reaches the deeper areas, or what is
yes, because that is a very fast process. It could be that first the autumn storms or so transport the big bunch. So resuspension is very intermittent. So it is just a few storms during wintertime explain most of the transport into the deep. So it could be that it takes half a year or even longer that the material from the coastal zone is transported into the deep.
So then even if the sediment focuses, most of the nutrients will have gone back to the water phase already.
Okay, so these were the processes in principle included in our model, and now I would like to take the last 3 minutes or 4 minutes, maybe 5, to introduce the model. It's called RCO-SCOBI. It's a typical biogeochemical model, so there's not really something special. Very many other models are working in the same principle. It's a 3-dimensional model that based on a 2 nautical mile horizontal grid, and here you have the state variables that I have discussed already. So state variables are nitrate, ammonium, phosphate, oxygen, negative oxygens, hydrogen sulfate, autotrophs, zooplankton. Maybe I have here a list. So inorganic nutrients, nitrogen fixation is included, particulate organic matter. We have 3 autotrophs, and we call them diatoms, flagellates, and others, and nitrogen fixing cyanobacteria. But these are really classes. So think each of these state variables are advection and diffusion equation plus sources and things. And the arrows here describe how you transform the nutrients, if you want, from one pool to another one. And then you have zooplankton, just one species. You have detritus, just one. You have 2 compartments for benthic, nitrogen, and phosphorus. Well, oxygen I mentioned already. Negative oxygen is hydrogen sulfide. The waves and currents I have discussed already, and resuspension. So these are the processes related to the sediments that I included in the model. And well, that was maybe too fast. So you can see here in principle what is included and what is not included. For instance, what is not included, if you want to build in the photosynthesis the autotrophs, we assume red-fit ratio, and we assume also that the filling up of the detritus is according to the red-fit ratio. So we have just one detritus pool. This is maybe not very good. Well, balsam, for instance, don't have this. And we are working actually to separate it, that we have it separately for N and P. But you can do it based on these very simple assumptions that you have just a reduced number of state variables, like shown here. Zooplankton, we really never looked at it because it's the highest trophic level, and the grazing of the fish is built in as a constant function on the zooplankton. So the variability, if you compare with observations, you should be a little bit careful. So this model is really, it's a, I would say, a nutrient cycling model. So it's to understand the uptake of nutrients from the water to the autotrophs, and then the storage between the water and the sediment. It's not more. So if you want to have a model that is more sophisticated, you need to put in much more processes. Okay?
I think I missed the benthic compartment there, benthic animal.
Okay. Yes.
They.
We don't have it.
Just a question. The resolution, so it's a 3D model. What's the terrestrial resolution?
3 meter, sorry, I forgot to explain. So the grid cell, it's a regular vertical grid, 3 meter from the surface to the top, to the bottom. So in total, in the deepest part, 83 vertical layers.
And then with the algae, you said you use growth ratios. You started playing around with.
Not in this one, but there are other models, flux models that are not Redfield. So these models are existing, but ours is a very traditional, simple model. Okay, and this we put in, we somehow summarize the modeling efforts. So you have here the processes included that well, impact the biogeochemical cycling. So of course you need to have an ocean model, a three-dimensional physical model, a three-dimensional biogeochemical model, and then you need the supply from the land, from the nutrients from land, and from the atmosphere. So this cannot be seen separately. Atmospheric deposition, all these parts are very important to include, and you need to have good data sets to get good results for the nutrient cycling in the ocean. So therefore, one can always argue, well, is it meaningful to add more processes into the biogeochemical modeling if you have just very coarse forcing data, for instance? And here is a sketch of the transport of organic matter in the horizontal, so it follows the overall stream function. Well, just to illustrate that the three-dimensional aspect and the variability in the horizontal is important. And if you are interested to read more, I believe the PDF for the PowerPoint here, and then you can read more what I think is important. And here you have also a list of data sets that we usually use in the Baltic Sea for evaluating the model. So both at SMHI, at the NEST Institute, at ICES and EMIP for the atmospheric deposition. And then I think I should stop. Thanks a lot. I would like to continue a little bit more about now applying this model. And one of the questions that we had is, or still have, is to investigate the combined effect of stressors. And in principle, I'm dreaming to include all stressors. So I'm by training actually a physical oceanographer, but more and more I'm not, and I'm not interested in biochemical processes in very much detail. I'm interested in the system itself. So some system research, understanding the interaction of the different boxes together. And that's the atmosphere, that's the land surface, the processes on land, that's the processes in the sea, in the sediments, everything. And so that's a little bit the motivation why we have chosen this kind of approach. And one big research question is actually to include different stressors and then ask yourself, what is the response of the system as a whole? And two of them are listed here, climate change and nutrient load. You can extend it if you would have higher trophic levels to fisheries, or you can add pollutions and whatsoever. Another big issue is that when you have these models, I tried to introduce you a little bit in uncertainties in the approaches. Like when you are doing measurements in the sea, the measurement itself has no value, but the error bar is the important message, right? And if you have a model, then you get just maybe one number, and then you know nothing about the uncertainty. I'm very much interested in the uncertainty of the model response as a function of the uncertainty in the processes in the model, or the uncertainty of the forcing, or whatsoever. One approach here is ensemble modeling, and finally then to use this model for practical applications like sea management, decision support for policymakers, like as has been done at the Nest Institute since many, many years, and that ended, well, not ended, but that accumulated somehow in the Baltic Sea Action Plan. So, therefore, it's if you do some forecast, and if it is projections, seasonal forecast or daily forecast, here it is the intention to do the projections for the climate, and the idea is, okay, climate will change on the time scale, say 100 years or 30 years or something like that. Or is expected to change. That's the same time scale that the Baltic Sea biochemistry would react to changes in the forcing, because the turnover time scale in the Baltic Sea is 30 years. So whenever you start now to reduce nutrients, you can expect during that time that you see the effects, also climate might change. So what we have done here is that in the center we have Baltic Sea biogeochemical models, coupled physical biogeochemical models. And to address the uncertainty, we have not used one, but we have used three. This is the one from SMHI, RCO-SCOBI. This is, so that's a three-dimensional model. This is Ergon from Germany, from the IOW in Warnemünde. It's also a three-dimensional model. And we have a horizontal integrated model for each of the basin, and then all the basins are coupled to each other. That's about some at the Nest Institute in Stockholm. So these three models has been compared. And then you need, of course, the forcing. What is it? Well, the atmospheric forcing and the hydrological forcing. And if you want to address climate change, the only information for changing climate is coming from global climate models. But these models are so coarse that they have maybe not included the Baltic Sea at all. So they are not useful. Therefore, these models are used to force regional climate models that have that includes the Baltic Sea properly. And then these models have output, atmospheric and hydrological output, runoff for instance, but you need really the land surface included to calculate scenarios for nutrients. And the same for the atmospheric chemistry. You need to know when you have certain emission scenarios how the nitrogen deposition is developing in time over the Baltic Sea surface. So there's a bunch of forcing models that are used to force these biogeochemical models. And then that I will not discuss further because I assume Susa will do it, or you have done it maybe. That the output from these biogeochemical modeling can be used for hydrotrophic level modeling. I told you the highest level in our biogeochemical model is zooplankton, but you can use for statistical modeling the output like temperature, salinity, like cod reproductive volume, like anoxic area. What I forgot?
Salinity, but you said maybe.
Yeah. Salinity, temperature, primary production. Yeah, these five. To force statistical models, ecopath, ecosim models, and to calculate what is going on the hydrotrophic levels, and so on and so on. So, and all this information you can then gather together and make a decision support system in the sense that you can judge what is going on under certain assumptions of nutrient loads. I will not talk about this part because that will Susa do. I will concentrate mainly here on this box, but this is a little bit the rationality behind. So where are the uncertainties in any kind of climate change projections coming from? Well, of course, the emissions. And you need certain emission scenarios. We do not know how that develops the future behavior of mankind. And that's both true for climate, so the emission of greenhouse gases, but also the emission of nutrients to the Baltic Sea. Then the models are not perfect. So for the climate model, it would mean the climate response to changes in atmospheric composition. And for the biochemistry, it would mean the sensitivity, if you reduce the nutrient loads, what will remain in the water column, and what are the time scales, and so on. How the pools in the water, in the sediment, react to changing external loads. And finally, natural climate variability, and there are two sources. One is for the climate scale, solar activity and volcanic eruptions that are forced and unforced climate variability, that is the internal variability generated by the nonlinear dynamics of the climate system. So whenever you address a certain time scale, it could be just by chance that the next winter is cold, although we have a global warming, right? So when you address the changes, you should make sure that you address long periods of time scale that you average to take the variability in the system into account. So typically, and a good rule of thumb is to compare future time slices of 30 years with present time slices of 30 years, taking the mean. And then you can do something like students' t-tests or something like that to calculate the statistical significance. If you have shorter periods, like 10 years time slices, you get immediately problems with significance. So this needs to be into account in this kind of modeling. So what we have done is we investigated a lot of models and a lot of different scenarios. So 4 climate projections for the period 61 to 2100, 2 different global models, 2 different emission scenarios for greenhouse gases, 2 different realizations of the climate behavior with the same model, so then there's just the initial conditions perturbed, that we can make some estimates of the natural variability in these runs. We have used several regional climate models. Well, I will concentrate just on one, but we have actually used 2. Several hydrological models. That's another big issue. I mean, you are all from the marine science, I assume. But the most important things are actually going on land, right? If you see the system as a whole. Hydrological models to calculate nutrient loads, it's a tricky thing because it's the interaction with the man, with the society that plays here into a role, how the drainage basin will change in time, how when it's warming, how the agricultural land and land use change spatially. So, for instance, the regions in the north will be used in the future that can today not be used for agriculture. All these kind of, and here are models, and they are well, at least of the same, have the same uncertainty as Baltic Sea models, for instance, because the processes there are not known as well. I told you already 3 Baltic Sea models. Then we have assumed different nutrient load scenarios. The Baltic Sea action plan as a best case, if you want, in this range, and then this one I skip here. The reference and the business as usual, and the wording here is very, very bad actually. Business as usual means here an exponential growth in agriculture, so an increase in the nutrient load. So decrease, increase, no change, simply. And then we end up with some 40 to 50 scenarios or different projections. And the idea is now, if you have all these different projections, you put them into one pot and calculate the ensemble mean. And the spread or the uncertainty you calculate from the standard deviation within the ensemble. So you get always an ensemble mean and error bar if you want. And the error bar is then reflecting, for instance, the uncertainty in global models, or the uncertainty in Baltic Sea models, or the uncertainty in greenhouse gas emissions, or whatever you like. If you put everything together, then everything is in the error bar included. So that's the idea. But before I show you some examples, I would like to come back to the comparison of these models. I told you we have two three-dimensional models, the one from SMHI and from IOW, and one horizontal integrated model with 13 basins, resolving 13 basins. The atmospheric forcing, so we started with a model intercomparison to find out if these three models are at all able to reproduce the period of, say, 30-40 years of present climate variability. So then we use the perfect forcing, and the perfect forcing is not existing, but what one can done from the atmospheric science to use an atmospheric model and assimilate all the available observations from the atmosphere into that model. And this has been done within ERA 40, so a real analysis, and we have these used as downscaling to force the Baltic Sea models. This is important because the Baltic Sea has a high sensitivity to the atmospheric forcing. And then we use this period as a validation period using data from the BET database. Yeah?
Within these three different models, what are is it mainly the resolution that is different, or are there very different processes in the biogeochemical compartments of those? What are you actually comparing?
So I would say the big differences between the two Swedish models is the physical part, that one is three-dimensional, one is one-dimensional. The biochemical, correct me, Barbara, I would say they are relatively similar. So we have, well, at SMHI we have looked what BNI is doing. So if they have invented a new process or something like that, then it's also included in the in our model. So they are very, very similar. Okay.
The German one.
The German, they have some details that are quite different. For instance, I will come actually to that later on. The bioavailability of the nutrients, the assumption, what of the external loads is bioavailable. Okay. So it differs in Sweden and Germany.
So if there are major biogeochemical things that might be really important, that is not included in this.
Well, in principle, the basic setup is also from SMHI, BNI, and IOW is very much the same. So they have also three autotrophs and so on. But some details in the assumption and in the interaction with the pools are different. And they make really the difference. But the overall idea is very much the same. Very much the sketch that I showed you before. Do you agree?
Yeah, I would agree.
So what we have done this evaluation simply at some stations, monitoring stations in each of the basin. We have selected 6 here in this comparison, and here are the results. So this is a little bit messy. You see different variables, the different columns: temperature, salinity, oxygen, phosphate, nitrate, ammonia. Then you have the 3 different Baltic Sea model, RCO-SCOBI, but some ergon in these rows, and the upper row is actually the ensemble mean. And the colors here, so you should see this as a section through the Baltic Sea. So a section from Anholt east, from the Kattegat to the north, to the Botnian Bay F9. So these are the station numbers. And here you have the depth. And the different colors here denote in the boxes that has been studied the mean bias simply. So if it is, and then it's actually divided by the standard deviation of the observations, so that you have a dimensionless number. So if it is red, the performance of the model is not good. If it is blue, it's okay. So, well, first starting with temperature, looks pretty good. Salinity, okay, maybe one model has a little bit problem with salinity, but otherwise it's okay. What you can easily note is that the ensemble mean is usually as good or even better than each of the members of the ensemble. So there is an added value to look at a multi-model ensemble because the mean is better than the individual components in the ensemble. And oxygen, okay, maybe also okay. But if you go to phosphate, there is in all models a problem in the northern North Sea. You can argue, okay, we divided by the standard deviation, and the variability in the north is much smaller in the south. This is a little bit like we have chosen the measure of what is good and what is bad. That is okay, but we got as an overall conclusion that the models really have problems with the processes in the north as well. So one can say, okay, these models are good for the Baltic proper and for the western Baltic Sea, but the Botnian Bay and Botnian Sea will need to be very careful. The biogeochemical cycling does not work so well. So maybe the new version from the NEST model is better now. But at that stage, when we did this comparison in 2011, all the models had problems here. Looking at another variable, hypoxic bottom area, which is quite important for the dynamics. You have in green the backdater, it's a function of time. Here from the 70s and the 3 different models. So they are doing in principle what they're supposed to do, but there are deviations. In this case, the one-dimensional model is the worst, and this is actually understandable because they can, because the spatial extent is not resolved. Otherwise, bottom is the best actually from the ensemble. So you can see somehow the dip during the stagnation period in the models, but they overestimate the observed hypoxic area in this case. So if you go now to projections, then you get figures like this. This is the integrated volume, integrated temperature and salinity. And the solid curve is the ensemble mean, volume average as I told you, and the standard deviation is denoted in the ensemble by the dotted and dashed curve. So this is the kind of error bar, and this is now not specified, so it is among all the models, all the Baltic Sea models and global models and so on. So you can say, okay, at the end of the century, this ensemble projects an increase from, say, 5-6 degree in the volume average to 8, but there is a range of uncertainty of at least ±1 degree, if not even larger, and the same for salinity, so salinity is going down. That was the purpose to do this kind of plotting here, that we have used so many runs. Another question you can ask yourself, okay, when is the signal statistical significant? When are we out of the noise? And the significance intervals are the straight lines. And you can ask yourself, okay, when is the solid line here coming out of the range of uncertainty? Well, you can detect it with this model system, with these uncertainties and assumptions behind and the natural variability earliest in 2013. Earlier it is not possible to detect the changing climate signal, and the same for salinity. So that's a new kind of thinking to build in somehow the uncertainties in the model. You can do it also in a statistical approach, of course, in the model, but here it's used in this way. So just to illustrate a little bit what is going on, that I can explain briefly the results. Well, here you have two of the projections. The warming signal, sea surface temperature changes between the future 30-year time slice and the present time slice. And you see the warming signal is largest in summer in the north. Why is that? Well, that's iso-albedo feedback. the atmosphere is warming and then the ice responds. So more of the solar radiation is then absorbed in the ocean, and the melting actually is accelerated. So we have first in the spring this largest signal in the southern basin. In average, this is the northern part is ice covered, so this vanished. And then in summer, well, it's actually basically June. The rest is warming up. These are two different projections from different climate models, and this gives you an expression of the an impression of the uncertainty. That in principle the signal is equal in the two global models, downscale global models, but so that we have the largest signal in summer and in spring in the north. But in detail, the colors say just that it can be quite different, and that's of course another issue to calculate the response. So we call this northern amplification in the Baltic Sea, but that is actually confined by present trends in sea surface temperature from calculated from satellite data. So to wrap up, well, no, not to wrap up, but to add a little bit more information to the nutrient loads. I told you Baltic Sea Action Plan and business as usual. One is a reduction, one is an increase. To the left we have actually the nutrient, the nitrogen loads, to the right the phosphorus loads, and here it's a sum of all the loads from the atmosphere and from the land. And so the reference is something here in between, and we have mean is ensemble mean and the plus minus 1 standard deviation. So this is also a little bit new thinking. When you do a model comparison, usually you assume, okay, we have different models, but we force it with the same forcing data set. But that is not done here, because there are different projections as actually forcing the hydrological model and calculating with them different nutrient loads. And then I told you the thing that the biogeochemical models have different assumption on bioavailability. So therefore the German model sees a different change in nutrient loads than the Swedish models. So therefore we have a range, all of them. So it's very clear that this is, well, improvement, this is an worsening of the eutrophication, but it's not one number in the forcing, in the change. It's a range. Also the forcing is a range. And this is actually, well, we tried to make it more similar, but it was actually impossible because the models are calibrated to the forcing data set. So the German model as it was at that stage could not be run with the Swedish forcing data. Okay. To the left, you have an example of one station. Again, Gotland Deep, the mean profile, ensemble mean for per period 78-2007, 30 years, compared to bad data, and it's reasonable well. And here you have the change in the different nutrient loads. Actually, the different colors shows the different scenarios, business as usual, reference, Baltic Sea Action Plan. And here you immediately see, well, the forcing is symmetric, or almost symmetric, if you compare these two. Well, it's not really symmetric, but almost. But the response is not at all symmetric. So even in the Baltic Sea Action Plan, we have a reduction in the oxygen concentration in the deep. So why is that? Even if it is improved? Well, okay, I show you also this one. This is the horizontal changes in bottom oxygen concentration changes, summer bottom oxygen concentration in the three nutrient loads, Baltic Sea Action Plan, reference, and BAU. So blue colors means that there is a reduction in the bottom oxygen concentration by -4 milliliter per liter. Red means there's an improvement by 2 milliliter per liter here in the reference in the Gulf of Finland and in the Baltic Sea Action Plan. And this lower figure actually shows, well, then again, the uncertainty. It's the signal to noise ratio. So the change divided by the standard deviation, and if it is smaller than 1, it's okay. If it is getting, well, it's not okay, sorry, the other way around. And if the signal is larger, so if it is getting greenish, then you can rely on that. So blue parts is actually not reliable information in these maps here. You see here's some red, but basically it is around 0, so the greenish and yellow colors in the Baltic Sea Action Plan. That was a little bit unexpected. I show you also the development of anoxic and hypoxic area. It is in the all increasing, even in the Baltic Sea Action Plan it is staying constant, but not much reduced. I'll jump over this. I'm now going to discuss more the processes. So what is the reason? And that's a nice figure from Bärbel. Maybe you want to explain it?
No, go on. Because it was such a long time ago, I might have forgotten what I did.
Okay, it shows for the different scenarios. Business as usual in red, reference, Baltic Sea Action Plan is again the sample mean and the range of uncertainties in the dotted curves. Primary production, nitrogen fixation. Phosphorus release from the sediments, nitrogen release from the sediments. Sediment phosphorus pool, ratio between release and phosphorus sediment pool, denitrification, and the ratio between denitrification and nutrient supply. So first, what is the main change? So the idea was actually to look at the fluxes between the different pools and to understand what might be the response to warmer climate, warmer water, and what might be the response to increased or reduced nutrient supply. So first of all, what you can see if you, for instance, take the red curve, the ensemble mean, and then here we have the dotted curve, and the other dotted red curve is here. There's a huge uncertainty in the fluxes. If you calculate that. So for the two scenarios where we have an increase or well, a basic increase in the supply, there's an increase in primary production. Nitrogen fixation is going up. The phosphorus release from the sediments is going up, but also the sediment pool, phosphorus pool, is in the red scenario going up, and even in the reference scenario. So therefore, it's maybe more important to look at the ratio between the release and the phosphorus sediment pool to learn something about the sediment turnover, and that is actually the turnover is reduced, so it's getting faster recycling due to the fact that the fluxes are temperature dependent, but the phosphorus fluxes from the sediment. And the same for denitrification, so it's going up, but the ratio between denitrification and nutrient supply is either constant or going down. So the very much important sink for nitrogen in the Baltic Sea is getting less and less effective in a warmer climate. Well, I can also show this one. One idea was, okay, can we rely on the response in the model for this kind of management scenarios? Well, we cannot really, because the period where we validated The models were 30 years, and there's some variability included that we investigated, but the projected changes on 100-year time scales are larger than everything that had been observed during the present climate for the past 30 years. So therefore, the sensitivity of the models, and actually it turns out the three models are quite different in their sensitivity to nutrient load changes, cannot be validated really. If you're not going back to, well, very long time back to a state in the Baltic Sea where the that has been oligotrophic instead of eutrophied. So therefore, we worked in that project with the reconstruction on very much longer time scale from 1850 until today. And this is a figure from Bo Gustafsson showing the reconstruction in the loads, phosphorus and nutrient, from land and from the atmosphere to the sea. You see that it was low in 1850, it went up with the intensification of agriculture and use of fertilizers. It accumulates in the 80s somehow, and then it went down again, and also for nutrient loads. For the atmosphere, it's less clear how to develop, but the reconstruction followed very much the riverborne nutrient loads. And here in the lower two panels we should see the winter dip and din pools in the Baltic Sea. So it's going up and it's actually not going down as not following immediately the reduction in the loads. So what are the models doing? And we tried to do this in these panels. So it's a little bit messy because there are a lot of different information. The first, this is one station, Bornholm, Gotland Deep again. It shows temperature in the surface and temperature in 200 meter depth at Gotland Deep. Salinity at the surface, salinity in 200 meter depth. Oxygen in 200 meter depth, and then the following, and the next are actually phosphate at the surface, winter time phosphate, January to March, and nitrate phosphate. So let's go back. Again, it's an ensemble, so the projection, now it's here the yellow curves, and the range of uncertainties in temperature is shown here. And the reconstruction is then the black curves, also three models, going back to 1850. And somehow for temperature it fits quite well. You get an impression, okay, here we have some kind of warming signal already during the 19th, 20th century. And then it's accelerated in the projection, so that fits together. It is quite difficult to validate these ensemble means on, or at all the different models, because if you go back in time, for the reference period from the 70s onwards, it's possible, and that are here actually the green symbols somehow hidden in the bunch of curves. These red symbols are light ship data, so we tried to manipulate them in a way that they fit to the model results, but it's not so easy because they are undersampled, no measurements, for instance, or less measurements during winter, and if you want to calculate annual means, it's very difficult. They are not exactly at that position, so we took it a little bit further to the north, so therefore it's basically the shift. So it is very difficult to validate the past somehow, but here's some kind of try, and you see, okay, maybe it's not too bad. And the same for temperature in 200 meter depth, and the same for salinity at the surface. So it seems from the past you cannot really guess any trend because there is none. But the projections show, okay, that is unprecedented change in future compared to past variability. In the deep, it's already a little bit more difficult because the range of uncertainty is increasing, and you see here the green dots from the observations, and this one is the inflow, the largest inflow that we are aware of in 1950. None of the models is actually able to reproduce this inflow correctly. So please keep that in mind. So here you cannot really say that this change is unprecedented compared to the past variability, or it's at the edge of, because of the larger interval of uncertainty. If you go to oxygen, the interval for the future projection is getting larger, but here is now coming in the uncertainty of the loads. Therefore, the different colors, red and blue, for business as usual and Baltic Sea action plan. So that is clear that there's somehow an increase in uncertainty. But there's also uncertainty in the past. And phosphate, well, it works also like oxygen, that you can make some statements about that the level wintertime phosphate concentration is larger compared to everything that has been observed before. But for nitrate, it's not possible anymore. So the models have here really no skill if you take this as an objective measurement. And that is actually, one of the models has a quite bad representation of the surface winter nitrate concentration in the past. It does not really follow the observations if you go back in time. So that's the state of the art. Just to wrap up this part, in future climate, increased loads and temperature-dependent rates of biogeochemical processes may result in an overall intensification of internal nutrient cycling, including substantial increases in both primary production of organic matter and oxygen consumption for its mineralization. Without drastic nutrient load abatements, hypoxic and anoxic areas are projected to increase, so it's unsymmetric. So now I would, the remaining part I would spend to my homework. What type of question is your modeling approach suited to answer? Well, coarse and large scale somehow. So the coupled three-dimensional physical biogeochemical cycling from seasonal to centennial timescales. Therefore, this kind of modeling approach is done. You might go to smaller than seasonal, say daily or so, but then it's already problematic with the forcing. It is not built for any more detailed studies of the food web or something. For me, ecosystem is something very abstract. I do not know really what that is. It's the cycling of physical and biogeochemical parameters. Okay, nothing more. Although we sometimes say impact of climate change on the marine ecosystem, but that is not really what we are studying. Which processes are not so well resolved with your modeling approach? Well, in general, all processes, subgrid scale processes like turbulence, smaller saltwater inflows, because of the limited resolution simply. Then a big issue is that really some big parts are missing, dissolved organic matter. We really have not developed that. This is underway. Carbonate cycling I've also listed here. It's a question if it is so important for the response of the variables that I've shown here. But of course there is interest in acidification and other things like light climate. We have discussed during the lunch the microbial loop already. Cyanobacteria, so what we are now working at SMHI is to include a life cycle model, because these simple description of cyanobacteria, it is possible in an integrated way to validate it, integrate it over the base and integrate it over a year, but there is no scale at a certain grid point in the model at a certain time. It's simply so. Etc. Because the list can be extended. More questions of like, how is model validation uncertainty addressed? Well, we have in the past very much worked with the multi-model assembler approach, like I introduced. There are other possibilities to have process descriptions in the model with some noise, so that's stochastic noise added that you can do. But other possibilities, but that is what I've done. What kind of data is needed to run your model? What type of output does the model produce? Well, I told you that we are working a lot with the system approach. That means that we use models to generate the forcing. So regional climate system models. So for instance, the wind speed is not observation, but it's coming from an atmospheric model. And that is, if you want to go back or forward in time, the downscaling from global climate data. So the output would be gridded data, 2 nautical miles times 3 meters in the vertical. Typical variables, okay, everything in the physics is listed here: water temperature, salinity, current velocity, sea level, sea ice. We have the quite advanced sea ice model with ridges and so on. And then the standard parameters in biogeochemical modeling: oxygen, ammonia, nitrate, phosphate, phytoplankton concentration, 3 autotrophs, zooplankton, detritus, benthic nitrogen, and phosphorus. That are our parameters. And from that we can of course calculate combinations like quadriproductive volume. Do you see any potential link between your modeling approach and other models? I think we have a quite good collaboration with Stockholm. Here we have an horizontal integrated model in Baltic, and the RCO-SCOBI is 3-dimensional. For instance, with this model you can do a lot more runs than with the 3-dimensional model. So if you want to test new parameterization, new model development, it's always good to do it in this model environment and then transfer the results into the 3-dimensional model and look what is the advection diffusion, the spatial component changing in the response. You are laughing, Bärbel, maybe nowadays Balsam is not so cheap anymore, but it has been...
It's still the same cheap. We
Okay.
run it actually here.
Okay, good.
It's online.
Also for 100 years.
Yeah. It takes if you do run from 1850 to 2006, it takes something like 15, 20 minutes.
Mm.
Something like that.
Okay, and that is very convenient that you can test certain things, and it's also convenient that you do a lot of ensemble simulations, for instance, at the same time. So that's an advantage, and the 3-dimensional model would then add sorry, all the complexity with horizontal transports, the coast, open sea interaction, and so on. What do you consider the biggest knowledge gaps in our understanding of the Baltic Sea ecosystem response to drivers as a whole? I put in this red here because to understand better the question. Salinity is a big issue in past and future climate, how that evolves. I would say I have not talked too much about that. But we are in a climatologic transition region that in warmer climate the south is getting drier, the north is getting wetter, so what overwhelms? And that is the same if you're going into the past, studying, for instance, the salinity in the medieval warm period. It is not quite clear, even if there are proxy data available. So, and also, what are the changes in saltwater inflows? Saltwater inflows are important, and we know that the big ones are less frequent today than it has been 30 years ago. There might be a regime shift from smaller to larger, from larger to smaller saltwater inflows. We have no idea why that happens, and if that is something related to changing climate or not. Then another issue, I think, lower trophic, higher trophic level interaction. With our model approach, we cannot study it really. We have tried a little bit, but that was, I think, not so successful. There are new models under development, these end-to-end models that can address actually these issues, but we do not know today how much is the impact of top-down versus bottom-up control. Feedback and the whole systems is not really well described, like the feedback between the climate, the land surface, the socioeconomic response, and nutrient loads. I have shown you here the results from very coarse and simple nutrient loads, this business as usual and Baltic Sea action plan. But this is not really the true story, because the land surface is of course interacting with climate and producing a different load inputs, and then this need to be related to management scenarios. So this is something more that the model needs to go to more system interactions. More plausible nutrient load scenarios consistent with large-scale development. It was really completely not related to large-scale scenarios, like for the IPCC, when these A2 and A1B scenarios have been developed, they have models for that, actually, how the greenhouse gas emissions are projected for the future. And you can assume, well, it would be consistent to have the same underlying storylines for these large-scale IPCC scenarios than for the Baltic Sea stuff. So to reduce somehow the uncertainties from the scenarios. And then my dream is actually to go more for multi-stressor approaches, to take other stressors into account that are also important for the response of the nutrient cycle. So this is some literature that I recommend. A special issue about this project called EcoSupport from last September. If you are interested, you can download it from the Baltic's homepage. If you're interested, I can give you the well, and then I would like to make some advertising. This is a conference on Öland from the Baltics program, Baltic Sea Experiment, and I added here Baltics and Baltic Sea Action Plan. Actually, the conference is the end of this Baltics program. And what we are doing at that conference well, it will be the birth of a new program, a successor program. And there will be very much more Baltic Sea issues and management-related things to Baltic Sea Action Plan included. So the theme is actually changes in energy, water, and matter cycles for the past 20 years. That is included in the former Baltics program. But then there will be also building regional Earth system knowledge, a future program for the Baltic Sea region. And I hope to see many of you at this nice conference, because we want to discuss how the new program should look like. Thanks a lot for your attention.